Okay, so we're talking about quadratic functions now, overview. So far at this point in Algebra A or Algebra B, you've seen linear functions overview and exponential functions overview. And so in contrasting here, linear functions would be some sort of a line. In exponential functions, it's a graph with an asymptote, some sort of an asymptote, usually the x-axis for general ones. And a quadratic, however, is a u, and this is what's called a parabola. And so it's a function that has a special property here that it's symmetrical about the y-axis. I didn't draw one here that's symmetrical about the y-axis, but in general, the generic one, y equals x squared, is symmetrical at the y-axis. And so this is a nice function here. It's something that you'll find out is involved big time with gravity. Anything that involves gravity, a ball being dropped, anything being thrown, anything being shot, anything that's being that goes through the air that involves gravity is going to be related with a quadratic function. So that's usually a big key, big giveaway that it's somehow a quadratic function. Okay, so these two tables here are linear and one is exponential. So in a linear function here, we're increasing by 2 every single time. So we're adding 2, and that's that constant addition that we talk about. So the first difference, meaning that the difference between 7 and 5 is 2, or we're adding 2. That's my son Samuel. Alright, anyhow, so we're adding 2 every single time, and so that's a linear function, and that linear function would be y equals 5 plus 2x. Okay. Now the next one is going to be, this one's going to be this is going to be exponential because we're multiplying by 2. So we're multiplying by 2 every single time here. So 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. And so this is an exponential, and this gives us the value of y equals 3 times 2 to the x. Okay, now this table here, this is going to be a quadratic. It's going to be for y equals 3x squared. So if you look at this, the difference between 3 and 0 is 3. And 12 and 3 is 9. And 12 and 27 is 15. And 27 and 48 is 21. So you might think, oh, there's no pattern here. Well, look, if you look again, let's turn this to blue. If you look again, if you look at this again, 3 to 9 is 6. 9 to 15 is 6. Oh, great, nice numbers here. 15 and 21 is 6. So anyhow, this constant difference here, they all have the value of 6. So if I wanted to create the next number, I know that the next difference here would be 6 also. So 21 and 6 would make 27. And so that means my next number would increase by 27, which then would produce 75. So it's another way of looking at the table. And this is what a quadratic table looks like. This here is called the second difference. The second difference is constant in a quadratic. It is not a coincidence that you have the x squared right here, that it's a second difference. When it was a linear function, it was the first difference. And you might make the conjecture that if it was a cubic, that it would also be the third difference. Okay, so we looked at the table, which shows the second difference is constant, and that's different than the linear function, where the first difference is constant, and the exponential, where instead of adding a constant number, instead it's being multiplied by a constant number. So that's the difference in the tables. Your generic in a quadratic is the generic one right now, ax squared plus bx plus c. So that is a quadratic. That's the generic quadratic. Now, again, anytime you see the words, like falling or something like that, or being shot, that yields a quadratic. Okay, because gravity is all about quadratics. It's if you were to take calculus, you'd find out why this is true, but actually that has to do with the acceleration of gravity and the whole works. So the big thing here is that anytime you see those falling or shot or anything like that, if something's been thrown, then that yields as a quadratic function. So that's an idea. Anything that's been bounced off the ground, gravity's going to be in play, so hence it's a quadratic. Okay, so some key vocab that you need to know as we go forward here is that vertex is the highest or the lowest point. So when you're graphing a quadratic, you have a graph that looks something like this here. Okay, the vertex is this lowest point, or if it was another quadratic and it was opening down, and it's a U shape, which is called a parabola. That's another key vocab that's not listed here, but that also has a vertex, and that'd be the highest points. So the way you've got a highest or lowest point, and that's indicative of a parabola or a quadratic. The axis of symmetry, if you're looking at the graph here, if you're looking at the graph of this quadratic here, the axis of symmetry is going to be this dotted line that goes through the vertex. Okay, now the vertex, how do we find the vertex? So we talked about the y equals ax squared plus bx plus c whole thing, and the b here and the a value are used. So it's negative b over 2a is how you get the x value. That's only the x value though, so it's not the y value. Okay, so now to get the y value, you have to take this value and plug it back in, and that will give you the vertex. Now the axis of symmetry is simply whatever x equals the vertex is. That's a vertical line, and so this is x equals vertex, and that is your axis of symmetry. All right, so when you're graphing them, there's a whole lot. There's going to be a whole other slide for graphing parabolas. But the idea here is that you have a graph that has this symmetry, and the axis of symmetry is this dotted line that goes up and down through here. That's the axis of symmetry. Now the end behavior is, where does it go off as x gets big and small? Is it infinity or negative infinity? Okay, so if your function was, say, y equals 2x squared, then it would go off to positive infinity for both directions. And the reason why it would be positive infinity is 2 is a positive number. So since 2 is a positive number, we have a situation where it's going off to positive infinity. Now if you had a function that was y equals negative 2x squared, then your graph would look mighty different. It would go off and go to negative infinity, and again, it is because the leading coefficient, or right here, is negative. That means it's going to fall as x gets really big or x gets really small. Okay, so there's 4 ways to look at any function, and for a quadratic function here that we have, we are looking at a situation for a quadratic. We have a table, and we already talked about the second difference is constant, so that we're looking at the table, and it's not like a linear function where the first difference is constant, but if you take the difference of the first difference, that's called the second difference, it is constant. Alright, so you have that situation there. The equation, you'll have an x squared, so we're talking about some sort of form like y equals ax squared, like y equals 3x squared, etc. Graph, you'll have a parabola. And a parabola is just simply a u that you're talking about, so that's something that, when you're looking at a graph. Now the story problem, gravity usually is in play. Alright, so this is going to be something that tips off that you're looking at a quadratic function. Okay, so we're going to get to our final example here. There's so much to do with quadratics, but just to get, a very general quadratics type of story problem. A ball is shot upward with an initial velocity of 120 feet per second and an initial height of 4 feet. Write the function. When is it at its highest point? Well, the fact that it's shot, or thrown, or doesn't matter, as long as the fact that it's involving gravity, then you have a situation where you have a quadratic. Now there's a formula that you have for anything that involves feet. It's negative 16t squared plus the initial velocity times t plus the initial height. Okay, so this is a generic formula that you have to know in terms of quadratics, because negative 16, this negative 16t, the negative 16 is half of gravity, so it's 32 feet per second is gravity, and so it involves that. So in our case, it's actually a very simple problem. It's y equals, automatically you have negative 16, because we're talking about feet here now. We're not talking about So the fact that it's feet per second, feet in here, then we're talking about that. Okay, so it's negative 16t squared, and it's plus because it's shot upward. It's not shot downward, it's shot upward. So it's plus 120t, and there's an initial height of 4 feet. And so you have the 4 feet there. So that's your function, y equals negative. Now, it's sort of tough to see but this is a negative right there. Negative 16t squared plus 120t plus 4. The question is, when is it at the highest point? That's the next thing. You could make a table and just plot a bunch of points and try to figure it out, try to approximate it. Well, the highest and lowest point always occurs at the vertex, and that's something, again, that you'll have is how to graph a quadratic, and those are the critical things. Those are the important things, the most important things. So I'm going to do negative b over 2a to figure out when it's at its highest. So negative b, which would be negative 120 feet, okay, over 2 times negative 16, which is negative 32. And so that would give you when it's at its highest. I don't have a calculator on me here, but that's going to be about 3.9 seconds here. And I know it's in seconds because in the problem here it's 120 feet per second. So it's right up here, it says per second, and so that tells us that it has to be in seconds. And so it's about right, 3.9 seconds. It's going to be, I know it's not quite 4 seconds here, so that's about correct. So that's when it's at its highest point. If I actually want to know what its highest point is, then I'd go back through and I'd plug in 3.9 in for the time. So this is just a general overview of what a quadratic is. We looked at the 4 different ways that you're talking about. There's 4 ways to look at a function. You have a table. The second difference is a constant. In that situation, the equation, you'll have an x squared. The graph, you'll have a parabola. And the story problem is, there's something usually where gravity's in play. It doesn't mean that necessarily gravity will be in play. There's other ones that involve area or maximizing profit and that kind of stuff that's a quadratic. But those aren't dead giveaways that those are quadratics. So this is a situation where see gravity or anything shot, then you know for sure it's a quadratic. Otherwise, we're not 100% certain. Other things that we looked at here, we looked at the graphs. We looked at how the leading coefficient's positive, it's opening up. Leading coefficient's negative, it's opening down. We talked about the vertex, which is the highest or the lowest point, which is right there. We also talked about the axis of symmetry, which is the dotted line that goes through the vertex. And we talked about end behavior, which is where the arrows are going. So if it's leading coefficient positive, it's going up, etc. And of course, here's your generic one, y equals ax squared plus bx plus c. Okay, so, and the big thing on the table, that your second difference is constant. From 0 to 3 is 3, 3 to 12 is 9, 12 to 7 is 15. But if you look at 3 to 9, that's 6, and 9 to 15, that's 6. That's what's called the second difference. And we compared it to linear and exponential. Linear, you're adding 2 every time. Exponential, in this case, we're multiplying by 2 every time. And if you went back to the quadratic, we are looking at the first pattern here. The first pattern of 3, 9, 15, 21, 27. Not quite obvious, but if you take it again, it's 6 all the way down. And you're looking at your different graphs. Linear is a nice line, and you're talking about an exponential, it's this curve, and a quadratic is a distinct U shape. So those are the 3 main functions you have to deal with in terms of your algebra. So, all right, I hope this has been helpful.